Okay, so last time we talked a little bit about the conservation of mass. So let's see. First of all, the people should start signing up for the journal club sign up. Maybe, so we're going to do some, we will do some group work at the end, but maybe just briefly, we'll go through, everyone maybe just say their name and their major and whatever there's, like what year they are and what they're studying. And we have 20 people, should get it in like 2 or 3 minutes. So just say your name and what your major is.
Hey everyone, my name is Daniel. I am a first year master's thesis mechanical engineering major, and that is it.
Yep.
My name is Saint. First year non-thesis master.
My name is Layla. First year non-thesis master mechanical engineering as well.
My name is Felix. I'm first year PhD bioengineering.
I'm Kelvin. I'm a first year non-thesis and master student in mechanical engineering.
I'm Ethan Weeks. I'm a second year master's student in mechanical engineering.
Don McCall, second year non-thesis master's in mechanical engineering.
I'm Clara. I'm a first year non-thesis master's in mechanical engineering.
I'm Raphael, first year master of mechanical engineering.
I'm Raphael too. I'm making a double degree with another school in France, and I'm doing a mechanical engineering master thesis. And I also work as an GRA in arterial thrombosis lab in the CoLab.
Paul, I'm also on a double degree program with my college in France, and I'm a first year mechanical engineering.
My name is Gaetan, and I'm first year in mechanical engineering master.
My name is Alper. I'm first year PhD student in mechanical engineering.
My name is Alex, and I'm first year student master in mechanical engineering.
My name is Ayo. I'm a first year PhD student in planetary science.
My name is Jacob, and I'm a first year PhD student in bioengineering.
My name is Chris. I'm a first year master's student in mechanical engineering.
I'm Elias. I'm a first year's master's student in aerospace engineering.
Good. So around the middle of class, we're going to do some of the index notation together. So I've got like 4 whiteboards there. So we're going to pass them out, and if you get, like, the people next to you get together in groups of 4, you can practice it. I think we'll probably talk briefly about the index notation. But we'll do that, I think, mid lecture. Okay, so the journal club sign up. If you were here last time, basically every Wednesday, and if we actually need to spill in some Mondays, people just talk 10 minutes about a paper they like. I think there are some people in industry that are online. Someone's gonna talk about the gas industry or something like that. But basically, talk about something that is fluids related that you can talk about for 10 minutes. And I gave a little rubric in the syllabus about choose how to choose the paper and things like that. And if you're really paranoid about choosing the paper, you can email me the paper and be like, it's like, what do you think of this paper? And I'll say, okay, what parts are good or what parts I think you should do or not. We don't want to do too much math in the journal club because, I mean, the rest of the class is basically math, and 10 minutes is not enough time to really even describe the notation and get into it. So really get into like the physics of why it's going on and show some movies. I wouldn't say it's supposed to be pure entertainment, but you should try to choose something that's not super boring. Okay, so try to, the journal club sign-ups on the syllabus. Choose a spot that you can do and start talking to the people next to you about having a group. Okay, so the first homework is not, I think it's due not next Friday, but the Friday after that, so in 2 weeks. But I've also given you, I've given you homework 1 and homework 2. They'll be due at different times. This lectures pertain more to homework 2, but homework 1 is kind of I wouldn't say it's a prereq for the class, but basically for you to understand lectures and some subtleties of the derivation, you'll need to know index notation. I spent a couple hours yesterday just redoing the entire homework too. So you plan to spend some time and also talk to people if you get confused. And I think we'll do a little bit of that today too, just to give you a jump start on the index notation. All right, so from last time, we talked about the conservation of mass. Okay, so last time we got to, let me look at one of your notes. Volume is, we didn't use divergence theorem yet, right? No, I don't think so. Okay, so we said we basically have this volume here, arbitrarily shaped, and a surface, and there's fluid flowing through it. Okay, and we said that basically we got to look at the time rate of change of mass in the volume. And that's equal to net flux through the surface. Okay. So last time, how much mass is in the volume? We wrote that as the integral, the volume integral in that, and that's the time derivative. And then we're looking at the flux. Oops, I have an extra term here. All right. So this is basically, you can consider this to be volume over time, unit-wise, and this is mass over volume. So clearly, the product of those is going to be mass over time fluxing to the surface. And the reason why we have the negative sign in front is just because of our sign notation that we have n to be the outward normal. Okay. All right, so that's where we got to last time. How do I scroll up? Okay. Now, this derivation, as well as the conservation of volume, we basically, as we talked about, fluids is like a continuum approach. So we need to go from integrals to statements that are true at a point. So basically, everything that's outside the integral, we got to pull into the integral. So since v is fixed, oh, why did it turn off? Push this button. Hey, Jeremy, do you know how to fix the front thing? Just for some reason it turned off. Maybe. Oh, does it have a start button? No. This Wacom turned off. Oh, okay. Maybe I just got to push it again. Okay. I think it's okay. Thanks. Thanks for coming in. So since the volume is fixed, we can basically interchange the time derivative and the integral. In first term. Okay, so when you do that, So that's 2 steps. Step 1. The other step is we're going to use the divergence theorem. Which says that the divergence of some vector quantity in a volume is equal to the flux of that quantity through the surface. All right. Across S and V. So together, we got d rho dt dv across the volume. That's a good question. What do people think these are partial or regular? Well, so for all these, so we got these field variables, rho, u, and they're rho, u, and u. Those are the ones. We're not even talking about pressure yet. These are the space and time. And anytime you have basically a function of 2 things, you got to use a partial symbol. So those would be partial. But yeah, my handwriting, my iPad handwriting on this tablet could be better. All right, so we're going to pull that derivative into the. Oh, good. People actually see my pointer. We pull it into this thing on the left, and on the right, we're going to go from this flux term to a divergence term. So together, applying those 2 ideas, we're going to get del dot rho u dv. Now this is good because they're both volume integrals over an arbitrary volume. So let's scroll this up. Oops. So let's put it all together on one side. Volume dt plus del dot rho u. So because the volume is arbitrary, we have our conservation of mass, which I think if you took undergraduate fluid mechanics, dot rho u. Oh, we don't even need the parentheses. All right, we have this. So this is conservation of mass, also known as continuity. All right. This does not, so if you took undergrad fluid mechanics, this is probably not the version you used, and this is not the version that I wrote at the beginning of the board last time, because it's got this steady state, it's got this time derivative stuff. Does anyone know like what the next step is to get this to the nice form? Yeah?
Great with respect to time.
That's a good idea, because we're trying to get rid of the time term, but we kind of already like had the integral, and we want to stick to the like differential equation form. Let's go through it. Let's go through it. So first, everyone expand this at your seats, and then see what we need to do. It has to do with our definition of incompressibility from last time. So let's expand this together. Plus, so you're gonna get 2 terms, and we will actually, if this is not absolutely clear how to do that, you have to do it for the homework. Prove how to expand this divergence. But you got 2 terms. So you got u dot rho del, oh, sorry, del rho. Okay, and just to be absolutely clear, rho is density, which is called rho, the Greek letter for, I guess, R. It's not P, which is pressure. So make sure you put little, I don't know, squiggly pigtails on that thing. U dot del rho plus rho del dot U. All right, so without having any assumptions, what we've shown is this to be the case. Okay. Does anyone remember, like last time, what we would kind of do to try to get rid of something? Yeah.
The term zero, because divergence of velocity is zero.
That's what. So that follows from an assumption. It is true, but it follows from. It has to do with the other two terms. Yeah.
That can be written as material derivative of the density.
Yeah, that's right. So last time we came up with this idea of material derivative. So this is defined as d rho dt. Remember, material derivative is for anything that basically this is the time derivative of density, not at a point. At a point, it would just be the regular derivative. This is following a fluid particle. We call that material derivative. And that's basically, you can't really do fluid mechanics without this idea, because the fluids are constantly flowing. We gave this idea of the skydiver. You know, the skydiver is falling, and he's sweating, but he's going over the city, so the air temperature might be changing. You've got to follow basically the convective derivative and the time derivative. And this is zero by incompressibility. So when we say that a fluid is incompressible, we mean that if I were to follow a fluid particle, you know, that density doesn't change. And that's not the same thing as that, like, the density is constant in space, because I gave the example last time of you could have a gradient of density. Like you could have a salt water that's heavier on one side, stratified fluid, and just because those are sloshing around, you know, they're still the same density, but if I follow the fluid particle, it's the same. But spatially, you know, if you've got waves, that density could change. Even if you've got like a tank of water with air, if you've got waves, hey, that's still incompressible, but if I look at a point, sometimes there's air there, sometimes there's water there. So you absolutely need this definition of the material derivative for us to talk about incompressibility. Okay, so assuming incompressibility, then we have basically the remainder, which is what we're going to use for incompressible fluids. So this is a continuity for incompressible fluids. And this is a version I'm going to use for Navier-Stokes. All right, I got to be a little more careful here. So for my fluid velocities, I'm going to try to use the U symbol, because there's so many variables in fluid mechanics. You don't want to use V because it's going to be mixed up with nu, and it's going to be mixed with the volume. So I just use U, and I'll try to stick with that the course. All right. So we're going to use this divergence of U be 0 for pretty much the rest of the class. Because like I said, if you're Aero Astro, then you got to use this full version. And you're looking at like waves and rho and stuff like that, but we're not going to do that. All right, so that is one of the four conservation equations. The other one is conservation of momentum. So the version that you have is basically follows from a lot of ideas about the strain field of fluids. So we're going to start with the Cauchy momentum equation. That's what we're going to derive first. equation. All right. Again, we have this volume V. It's got a surface area S. We got fluid going through it, and this idea of the outward normal. And we're going to basically do Newton's law, second law, on that uncontrolled volume. And we will take, I think we'll take a break halfway through to look at the index notation, because you'll need index notation to do one of the steps. And that's when we'll do the group work. So Newton's second law applied to this control volume. F equals ma in this case. Ma is like this part across the volume integral, and it's the sum of all forces. And we can separate those into body and surface. Oh, that's terrible. Forces. Okay. Body forces, gravity, surface forces, surface tension, things like that. So the word statement of this is the of So we got the rate of change of the momentum within the volume. And then we've got the rate of inflow. So that's the net rate. So you have inflow and outflow of momentum through the surface. Plus the body forces. And plus the surface forces. Okay. All right, so let's put all that together. So this is the first term we had on from Newton. We're basically going to split this material derivative into the two parts. One part's the time derivative, and the other part is going to give us this flux term, just like we did for last class. All right. So I'm introducing a little notation here for how we're going to talk about these surface forces. Let's draw a little picture. So if we got a normal vector here, we got this tangential t vector. So T is going to have the units of force per area. And the reason we will have this notation is we write it to remind us that it depends on the orientation of S. Yes. All right, so we'll consider the outside of the surface to be the plus side and inside the surface to be inside the body, the minus side. So this T as units of force per area, so T times ds is the force exerted by the kind of the outside on the inside. Yeah.
Stress vector depends on blank of ds. What is that word?
Orientation.
Orientation.
Orientation of let's start over.
Thank you.
So it depends on what direction ds is pointing it. Okay. And the surface force, it can have both normal and tangential components. Even though it's T, not necessarily tangent, that's just the stress on the surface. And we'll show for a Newtonian fluid how it depends on the density and velocity. On U. So we'll go like we did before. We'll move the time derivative into the integral. The only difference here is we're considering the quantity rho times u, not just rho. Okay. We apply divergence theorem again. So what does that look like? So divergence tells us the flux of a quantity. In this case, the last time for constant mass, the quantity was rho. Now the quantity is rho times u. So last time we were tracking the quantity of how much mass per unit volume is going through. Now we're tracking how much momentum per volume. That's what this is. And so this will give us del dot rho u u. All right. Now this is where the index notation is useful. So rho u is not a vector. That's a tensor. So that means if you imagine in 3D space, it's got nine components. Let's talk about how we need to. The next step, we need to simplify this. And you really can't get through this course without learning the language of index notation. So we're going to take a break and talk about how we're going to actually do this. And this will also be the subject of the next quiz, like how we basically go through those terms. So in some ways, this is a break from the notes, or you could consider this to be like a sort of a. We're gonna pass out these little whiteboards.
Can I ask you a question?
Yes, Jeremy. Oh,
Yeah,
is that JJ?
Yeah. Hey, I sorry, I heard you ask last class if you could hear us, so I guess that you can.
Yeah. So that voice of God you're hearing is someone from the Q section. Hey, JJ, how many people are there on the Zoom?
Looks like there's 3 other people besides me.
Okay, it's a party over there. Okay. Yeah. Do you have a question, or are you just testing the sound?
I was just wondering why, since the volume is fixed, then why can you take that derivative inside the integral? I was wondering if you maybe explain that a little.
Yeah, sure. If the volume were changing in time, you'd have to take that into consideration. But if it's fixed in space, the only thing that can change this quantity is the ability of rho and u to change at the individual points. Because we're looking at the time derivative, right? So I'm going to use my pointer. We're looking at this time derivative. If v, let's say if we were at some bad case, v were a function of time, you can't do this. Like if v were deforming and stuff like that, you have to keep it this way. But because the volume is, eventually we're trying to shrink this down to a single point. Volume is fixed. Because volume is not a function of time, the only things that are a function of time are these two, rho x of t and u x of t. So basically we can bring it in. Does that help?
Yeah, that makes sense.
V not v of t. Okay. Okay. Any other questions about, so we're basically going to spend, this class ends at 10:45. That's what we got wrong last time. We're going to spend like 20 minutes talking about index notation and working in groups. All right, so, yeah,
We should have surface integral.
You're right. Thank you. Wait. Yeah, divergence theorem. No, I think it's volume. Because what is divergence theorem? Let's go back.
On left it's S and ds, no?
Let's go back to the divergence theorem. Said this, right? Divergence theorem says this. So we're basically going backwards from the divergence theorem. It says that basically the flux of some quantity f is the divergence of that f. And here, like we're basically dealing with this term. Oh, I guess we're dealing with this term, right? And we're trying to turn that into a volume integral. So I messed up on this one. Maybe this is what you were trying to tell me in the first place. Sorry. Is that better? Okay. Yeah, we're basically applying the divergence theorem backwards to make it into a volume integral. I'll find a pen later. All right, so let's take a little. So, okay, the reason why we need index notation is how do you deal with this term? I'll tell you what the answer is, and this is how we're going to get. So we need to show. So this is exercise. Show the following identity: del dot rho u is equal to 3 terms: u dot del rho plus rho u dot grad u plus rho del dot u. All right. So let's do that. Let's understand the parts to do this, and we're going to spend 20 minutes to do this to do this together. Okay, and so this is a grad rho, grad u, and divergence u. So we'll call this grad rho. This is a divergence u. Let's just write it out. All right, okay, raise your hand if you started doing the index notation. Okay, raise your hand if you have not opened the PDF, the index notation. It's okay, index notation PDF. Okay, I'm going to guess pretty much everyone else who didn't raise your hand. Let's talk about this. So, Einstein index notation. That is the Einstein with the big hair. Basically, what did he? Let me get out my notes here. I don't want to spend too long, but I think people should get up to speed because basically by next week we should kind of starting the homework. Okay, he said he basically derived this in 1916, and he said basically what it does is for 3D vectors. It suppresses the summation sign every time the index occurs twice. Okay, so he basically suppresses summation sign every time index occurs twice. All right. It's crazy that before Einstein, they were just writing the summation sign. Okay, all right. So let's do some of the basic. So what I would suggest you do for this, you basically the handout. Do exercises. Do the exercises until page. Basically, the 64 to, really 64 to 74. All right. And let's talk a little bit about this together. All right. All right, so the other reason to use Einstein notation is basically for 3D coordinates. Because for example, the whole reason why this is a mess, why we have like this del and these things, is because everything is a function of x, y, and z. Okay. The other thing about Einstein notation, we're not going to be using x, y, and z. We're using 1, 2s, and 3s. So x, y, z. We're going to label those as 1, 2, and 3. 3. Okay. So this will be called E1, for example. All right. So for example, this is the vector A, arbitrary position vector A, A1. You could write that as the sum of each of these vectors, A1, E1, plus A2, E2, plus A3, E3. Einstein said, hey, you could write that as like this, AI sub E sub I. But I don't really want to write all this stuff, so I'm just going to write it like this. AI, EI. Okay, and the sum, anytime I've got that subscript I, I'm going to say anytime that I is repeated. So remember that I occurs twice. Twice, I. That means I'm going to sum across that. Okay. And remember that I is a dummy index, so it could also be J. All right. We've got a few. So maybe we should let's do the first problem from the homework together. Okay, so for example, delta ij times delta ij. That's the first problem of homework. So delta ij. So delta ij is the Kronecker. We call this the Kronecker delta. All right. All right, that's the definition. But physically, what it means is that anytime I've got I and j to be the same, like I and j are both 1, they're both 2, and they're both 3, the term stays. Every time I've got cross terms, it means that those terms disappear. Okay, physically, that's what that means. All right, so okay, so this is a little too hard. Let's do baby steps. So delta I. Let's figure out what that is. All right, so this is a good time that we're starting to, yeah. Kronecker, it's a German guy. Kronecker. Is it Kronecker? Oh, whatever, it's a German guy. I think it's a German guy. Kronecker delta. Kronecker. Okay. All right, let's pass out the little whiteboards. I thought I walked in. Oh, they're there. So we've got 4. So roughly, we can split the groups into like 4. And we have, I think I'm actually going to give it to the middle, these middle people. Because the people in the front, we can give those whiteboards. All right. And then you're going to have it in the back. But we're going to go through these exercises together and talk about it. And you people in the front, you can elect one or two people to be the writers. Ooh. And I don't know where you want to put it. And we've got one here. I got pens. Maybe you want to space out the table a little bit so you can go in and out. I don't know. Here's pens. And I've got a lot of erasers here. So we're going to work out a couple problems together on the board. Pens here. Hey, Chris. You guys need pens here? Here you go. All right. Yeah. All right, so do delta II. Tell me what that is. Let's do that first. And you can, why don't we space out, I'll give you a few more pens. We'll space out the tables a little bit so people can walk in between. And if you're at home, do it. If you have a mirror or something, do it, and then you can share screens. Actually, I haven't logged on to Zoom. Oops. All right. So remember, anytime I appears twice, it's like basically there's a summation sign there. And I goes from 1 to 3. There's 3 possible values for I. Because we're in a 3D world. And let's alternate the people that are writing, too, for each problem. All right, we got 3. All right, if you're done with that, why don't you do the next one? Let's see. If you're done with that, do the homework one. Delta ij, delta ij. Is that the homework? Yes. If you have a question, raise your hand and I'll come over. Yeah. Yeah, there's a couple in the front. Okay, what's going on? What's going on here? Is that a 1 or a 3 or a B? Oh, you're going to reuse the eraser too. Yeah, yeah. That's fine. I'm going to write a thing about it. Why don't you start the second problem? Delta ij, delta lj. Good. Good. That'll get there, but if there's too many people here, one person can go up to that front one too. If you can't see this. If there's too many people here, you can go up to the front one too. Or you can move your chair. Good. Okay, good. All right, let's talk about this, and then move on. So there's also side things, so you could leave stuff there. All right. So let's stop for a second and talk about ETGs, so we're on the same page. So remember, anytime there's two of the same index, it means that there's an implicit summation. Okay, so that means we're basically going to do I equals 1 to 3 of delta II. Okay? Einstein just said, hey, I don't need to write this thing because it's just repetitive. So basically, I is going to cycle through the following values, 1, 1, 1, 2, and 1, 3. So we have delta 1, 1 plus delta 2, 2 plus delta 3, 3. And that's the only thing we need to consider because it's delta II, right? And each of those is 1, so we got 3. So you should get 3 for the first one. The second one, it's kind of like now you have this is two summations between I equals 1 to 3 and j is 1 to 3. Okay, but it can only be we're considering the product of these two, and so you can imagine you've got 9. I mean, if you were really be pedantic, you'd have 9 different terms, but imagine the only ones that remain are when basically you have them all I and j to be the same. So this is 9 terms, but only remain if I is equal to j, right? Right? Because that's the only way you can get them not be non-zero. So that basically is going to give you, so this should give you, in other words, you have delta II, which is again 3. Okay. And you could count that on your own if you did want to write all 9 terms. You can imagine they're all going to, the only ones going to stay are the ones that are there. Okay. Let's stop for a second here. Do I need to write? Do we need to go through this delta ij more, and write them all out? Do people get the understand this summation notation? This is totally the time to answer the questions. Yeah. Yeah. Let's do it. Let's do it. All right. So these are summations between I and j. They're independent summations. So we'll start with, so basically we have delta 1. We'll start with I equals 1 and j going 1 to 3. So delta 1, 1, delta 1, 1, and then we'll change, delta 1, 2, delta 1, 2, plus delta 1, 3, delta 1, 3. So this is basically, this is for I equals 1, and that was all the j's. Delta 2, 1, delta 2, 1, delta 2, 2, delta 2, 2, delta 2, 3, delta 2, 3, plus, plus. Now we change the i's to 3, delta 3, 1, delta 3, 1, plus delta 3, 2, delta 3, 2, plus delta 3, 3, delta 3, 3. So everyone gets killed except the diagonal, right? Because everyone else has something that didn't match. The I and j were not equal, so that's why you only get 3. Okay? I'm glad that you asked that we do this, because this is the time we're together, and I would rather us spend like 3 minutes here than like an hour at home just being confused. Okay, and the big picture from that problem is they're two dummy indices. I appeared twice and j appeared twice. Therefore, we have these two different summations. Okay. All right, so it's 3. All right, the next problem. Let's see. Delta I j. All right, let's do this one on the homework together too. Hold on, maybe I might have. We need to start introducing the epsilon notation. All right. So we understand this idea of delta, which is basically important for dot products. Yeah. Uh-huh.
For the 9-block terms that we just did for the I equals 1 row, because the first, actually, never mind. I misinterpreted the question.
Yeah. So delta, I mean, there's the equation, but then there's what it does. What it does is basically, anytime the indices are the same, it stays. Everything else is killed. So you only consider the ones that are the same. And they've got to be the same for both of them.
When I was looking at the original question, I thought it was delta II times delta ij. It's actually delta ij times.
Yeah. Okay, so this is a good point. Let's say you had a problem like this, I times delta ij. You wouldn't really be able to, I mean, this would just turn out to be delta ij. Because the j doesn't have a second index, so you wouldn't be able to do the sum. So you wouldn't be able to simplify this to a normal number. All right, so why do we introduce this delta index? It's because it's for dot products, basically. A dot B, we know that to be A I E I dot A B B I, sorry. So every time you introduce a new vector, you should introduce a new dummy variable, bj, ej. So I'll write that down. New vector, new index. All right. And you know, basically, like A1, the E1 times E2 are going to be 0. So this is going to be something like A, I, B, J, and then the E, I dot E, J. This thing is just the Kronecker delta. A, I, B, J, delta, I, J, and then et cetera. Eventually this becomes A, I, B, I, right? Because delta I, J only gives you something if I and J are the same. So that's basically, every time you see a dot product, you should think, because of the Kronecker delta, you get this thing. So the Kronecker delta arises from dot products. All right. Now, if you look in the syllabus, we're in the middle of the course, we're going to be doing spin, angular momentum. And in fact, Navier-Stokes, for it to look so nice, is because of the symmetry of the problem. And we actually have to derive conservation angular momentum to get to Navier-Stokes. So cross products use the following notation. All right, let's say we have if you remember this rule, okay, so let's draw this one more time. 1, 2, 3. All right. E1 cross E, let's just keep it perfectly general first. EJ, E1 cross E2. Does anyone remember what this should be? Based on this coordinate system, if this is E1. Yeah. E3. Yeah, E3. And the issue is you could have, it depends on the sign. So E2 cross E1 is going to be negative E3, right? And then you have all the other ones. Now, Einstein said, hey, I don't want to write all that. I just want to write it like this. EI cross EJ is EK. All right. So he introduces this new symbol called the permutation symbol. All right. It basically has all, there's like a 2 times, there's like at least 6 or 8 different combinations to get the different cross products, and they're all contained in this. Okay. And this is again for I equals 1, 2, 3, J is equal to 1, 2, 3, and K is equal to 1, 2, 3. Okay. The permutation symbol is defined by the following property. It's 1 or negative 1 if I, J, K are different. Oh, that's terrible. And it's 0 if any index is the same. So for example, if I've got epsilon 1, 1, 3, it's going to be 0. And physically what that means, it means if I have E1 cross E1, there's no area between those two cross products, so that would be 0. Okay. It also has some other nice properties about like the even and odd permutations, and also the cyclic interchange property. I don't really want to write those up because they're getting kind of. Let's write them up if we absolutely need to. All right, so A cross B. We're going to write that AI. AI EI cross BJ EJ, and we're going to call that AI BJ EI cross EJ, and we're going to call that AI BJ epsilon IJK. These are supposed to be lowercase epsilons. EK. All right. So because you can imagine there's this tiny little summation symbol in there that's going across i's and going across j's, and there's this other k vector. All right. How far do I want to go on this? All right, let's warm up together. Let's use that notation to solve for this. A cross B cross C. There's 2 different identities for how we can change this. So when you at your seats with your partners, use index notation, and maybe one person bring out the PDF because there's a couple different rules called the cyclic and interchange property that I only really want to go over in the front if we absolutely need to, because it's like getting a much. So someone pull out the PDF and solve for this. So I'll tell you what we're going to solve for. This is going to equal to, and try to switch who's writing. We're trying to show that using Einstein notation. So I'll start you off with the first step. We go from left to right, putting indices wherever we want. And I personally like to start with i's, proceed to j's, and then k's. So here we've got AI, EI, BJ, EJ, cross CK, EK. Okay, and now you got to, because of that cross product, you're going to have to use the permutation symbol. Here's an eraser. I don't know if I gave you one earlier. Yeah, you're going to use the epsilon, the permutation symbol.
Oh, wait, say that again? So, yeah. You can just equal to, I mean, when you just
I would expand this one first with the epsilon symbol. Yeah. Expand the cross product with the epsilon symbol. Yeah. It's more complicated than that. Wait, so let's see. You did, let's see, the dot product. Okay, so you have this, EI. Okay, yeah, that's and this is good. So now, explain how that could be equal to those two terms using the cyclic and interchange property of epsilon.
Okay, but is this like the most that this can be simplified?
Yeah, it is.
Okay.
Yeah, the rest you have to. I mean, if you want, you could go backwards from those bottom terms and up, but you think about what those bottom terms should look like.
So I do think we go from there. We go from here.
Yeah, that looks good. Now you got to use the cyclic and interchange property. Do you know what those are of the permutation? Yeah. This looks correct. This looks fine. Yeah. You basically use the delta there. Okay. All right. Let's. All right. I see some people starting to zone out, so let's just go over this. All right, this is what you should be getting. AEI dot. Here you have BJ, EK. EL. So when you have the J and K, you want to introduce a new vector L, EL, so it go like this. And then basically you have the fact that AI, EI. So you have AI, BJ. This is terrible. CK. You have all the coefficients in the front, and then you have epsilon jkl, and then you have ei dot el, and this is the Kronecker delta delta il. And Kronecker delta means every time you see L, you replace it with I. So you might as well just stick with the original variables. So this will be AI, BJ, CK, epsilon, JKI. So this is as simplified as you can get, actually. Now, how in the world does that equal to those other two terms? It has to do with these two properties of epsilon. So let's talk about epsilon. Epsilon ijk is 1 if they're even permutations of 1, 2, 3. So the following are 1. Epsilon 1, 2, 3 equals epsilon 3, 2, 1 plus epsilon 2, 3, 1. An even permutation means you switch a term twice. So, for example, here, epsilon 1, 2, 3, I'm not switching any term. It's 3, 2, 1, I'm switching. I'm switching 3 and 1. Yeah. Yeah. So, for example, 1, 2, 3. I go 1, 2, 3. I go. How am I going to do that? I go 3, 2, 1. Oh, I made a mistake here. This is 3, 1, 2. Sorry. 3, 1, 2. And then I'll switch again, and this will be 3, 3, 1, 2. So there's 2 switches. Okay. Then as other property, it's -1 for odd permutations. Okay. And it's got 2 other properties. Let's see. Cyclic property. That means if I cycle stuff around, it'll stay the same value. ijk is equal to epsilon kij is equal to epsilon jki. Okay. And this is the interchange property. The sign changes. Epsilon ijk is equal to epsilon negative ikj. So if I interchange 2 of these, then it's going to change sign. Okay. Or epsilon ijk is next to is equal to negative epsilon jik, where I've switched these 2. All right, so the cyclic property and interchange property, that's why a lot of your derivations in this homework are going to be 0, because if you switch it and it becomes a negative of itself, it means the only way it could possibly be true if it's 0. You'll see that happening over and over again. All right, so how in the world does this equal to this? Well, that occurs from these different properties. So first of all, this one, let's make it into a term, something that we're a little bit more familiar with. Class ends in 4 minutes here. Where am I? So you could write this as epsilon jki from the interchange. We already did that. You also write this as epsilon ijk ai bjck, where we did the interchange. And this term, so each of these terms are different. This one is a you got to look at these first two indexes. We got I and J, so these go together. So there's A cross B dot C, right? Because they both have I and J. And these, this is JKI, so this is B cross C dot A. Okay. Because of the order of this index, here we got JK, because this is the definition of how epsilon works. All right. All right. We got 4 minutes. I do want to introduce you one identity that you're going to need to use for the homework, and I have a suggestion to make it a little bit sort of easier to deal with. All right. So this is the identity. It says if you got two permutation symbols together, you can simplify that to the following. All right, and this is identity. I think there's an explanation for why this is, but this term on the left is 81 different terms, and you could write them all by hand, but there's an explanation. If you look, there's some patterns. So the way I would do this is note that they're basically you're basically doing a summation across two different indices. How do I want to explain this? The way I think about this is that there are three indices here. So this is the first term and the second term. And then basically the way I write these, I kind of write it the following. So I'll write it be 1, 2, and this will be the first term, and this will be the second term. Delta 1, 2, and then I'll do delta 2, 3, 2, 3 minus delta 1, 3 times delta 2, 2. So for example, IL is the first term on the first this first epsilon, and then L is the second term on the second epsilon. Delta JM is the second term on the first one and the third term on the second one. Delta IM is the first term on the first one, third term on the second one. Delta JL is the second term of each. Okay. But you'll need to use this to solve this one on the homework, which is epsilon ijk times epsilon kji. So see if you can use this technique. Oh, we got 1 minute. I guess do it for homework. I'll stick around. This is the commencement of office hours. If you found this very difficult, I would suggest maybe you stick around and try to do this problem. We try to do it together. Otherwise, Monday I'll assume that you've done as much of the index notation you can, and we're going to go back to the proof, which involves index notation on this thing. And we will have a quiz on index notation in 2 weeks. If you ever miss a lecture, I've made a Canvas so that I think people can attend the Zoom, and people can also look at previous Zooms. I don't know what the quality looks like. It should be pretty good. Okay. But there's some subtleties like the stuff on the board, the group work you won't be able to do on Zoom. And if you're on Zoom, I can't actually see what you're doing. What's up?
You could move back down. I missed when you switched the epsilon from the back to the front.
This?
What was involved there? Yeah.
This term?
So you had like EJKI.
Yeah. Oh, how do I go from here to here?
From here to here.
Okay. That is the
No, I mean, I understand that this is the same as this.
okay, you understand. Yeah.
Okay. But and moving it from front to back doesn't.
No, because that's commutative. Yeah, multiplication is commutative. So the order, these are just products. When you're doing cross products, it does matter, but here they're just regular multiplication. So that's why this is a product, just like A times B times C. Yeah.
But these two things are the same.
Yeah.
This and this.
Yeah, I've used what's called the
Exactly.
cyclic property.
Okay.
That means like JKI, I can move that I over here to be epsilon ijk.
Okay.
Is that plus supposed to be an equal sign, or?
Which plus?
Epsilon 312 plus epsilon 231 equals 1.
Oh, yeah, sorry, there's an equal sign. Those are all equal signs. Thanks. This index notation, I would say you really, but try to work with, if it's confusing to you, work with a partner, but I think talking it out and just thinking about it, eventually you're going to get to the language of it. And I will stick around if people want to do this one on the homework together. But you basically want to apply that notation, apply this identity. Oh, the whiteboards, if you could just clean up and stack against this wall. Those are actually my personal ones that my wife helped buy me. So we're going to put them in the back, and I'll try to bring them to every class we do group work. And if you did stuff on the front, if you could erase it before you go, and bring your markers and erasers and put them in this pile. Uh-huh.